Okay, then we should start the discussion on the zero order system that we started in last class. So, if we recall, am I audible? Say, if you recall the standard procedure we found to get the dynamic characteristics known, we are first of all going to have the equation of the system. The input-output correlationship is obtained first, and then for the standard input, we are going to observe what will be the response of the system. And if the response is not as per the requirement or the desired, say, if the response is not as per the desired values, then we are going to apply the compensation. So this thing we have seen. And with this understanding, we also seen that it is very difficult for the characteristic estimation, dynamic characteristic estimation of the system if we have got multiple inputs. So as per the process of a calibration, we are going to apply the standard signals to it, and then single standard input is applied at a time, and then we are going to study the behavior of the system. So this was the first say thumb rule, or we can say the limitation. And the second one is we also know that the assumptions during this kind of calibration, that all the static error sources have been say anticipated, the correction is applied, and it is now assumed that there is no static error present into the system. All the static errors, including the say bias and all other components of the measurement devices, have been found out and applied with proper correction. So that calibration, static calibration is over first. Then only you can assume that there is no say role of any static properties there is no role of the static characteristics for into the dynamic characteristic estimation. So now with this understanding we have moved further and we have found that the zero order system is one where the coefficient other than the A0 and B0 are not present in the generalized model. Then we call that as a zero order system. Say for example A0QO is equals to B0QI. So that was the correction that we have made, and then we can find that ratio of B0 upon A0 is the static sensitivity, and we have seen that the static sensitivity is nothing but the slope at any instance of the time for the input output characteristics, right? So here very clearly we can understand that the input is on one of the coordinate and the output is on the other coordinate, and we find that the standard input when given is going to be the sensitivity K, called as static sensitivity. Then this also gives the ideal or perfect dynamic response. That's what we have studied. Why it is so? Because there is no error present into this. There is no lag, there is no delay, right? Whatever input applied at that particular point of time, having little change because of the bias or sensitivity, the output is reflected into the display of the measurement device. So this is very ideal and gives the perfect dynamic response. So irrespective of the value of the input, let it be the sinusoidal input or say ramp input or the step input or any other kind of the input signal that has been applied, like with the intensity variation or the frequency variation, output follows the input very truly. That's what we have studied, seen in the last lecture, right? So there is no distortion, there is no time lag, there is no change in the signal, right? So again, the signal form is not changed, as we have discussed in the last lecture, that there are different types of the signals, the periodic, aperiodic, transient, and the random signal. So we found that there is no change in the output signal with respect to the input in case of the zero order system. So this also we have seen. Then we have seen the example. Potentiometer is nothing but a simple example for a zero order system where the output EMF is proportional to the displacement of the slider, linear displacement of the slider, and that is what we have seen in case of our practicals also. Right. So this is little repetition of the yesterday's class. So here we found that the characteristic equation for the potentiometer as a measurement instrument or measurement system will be given in the form of the output is equals to the ratio of B0 by A0 times Qi, where K is nothing but again the static sensitivity of the potentiometer. Then the output EMF will be proportional to the Xi by L times EB. So this is nothing but K times EB. And then the input output characteristic can be given, say, as the displacement of the slider over the potentiometer goes on the x-axis in terms of L, we find the output EMF generated will be in terms of EO, is a linear proportional with the value of the sensitivity is equals to K. So this K is nothing but ratio of the output, the constant for the output, that is say B0 upon this as A0, right? So this is what is shown, the device. In this one, the external circuit is applied with the input EMF here, where the length of the slider, total length of slider is capital L, and as we go on changing the value of Xi, we find the proportional output EMF is induced. So potentiometer is very simple example of the zero order system. Similarly, the deflection in the spring, we can find the similar characteristics. Say if there is a spring and we apply some weight here, then the relationship between the input and output will be seen this as a very linear relationship. So here also the static sensitivity K is more or less going to remain same. That is what we find, and say theoretically we assume that K is going to remain constant for the complete duration of say a complete range of the reflection for the spring. Right. So there are few more examples. You can go through the textbooks and you can find out few more examples for the zero order system. So I think this also has been discussed. If there is change in input, say for example, step input is applied to the potentiometer, some initial value is given, then we find that the output also follows in the same way. It is K times QIS is the output given, and even if we apply that with the frequency response, we find the output remains the same. It is say more or less matching to the rate at which input is applied. Okay. So this is also seen in the last lecture. More or less this is going to remain constant with the value of K. Okay, so this is assumed to be very simple and is very easy to understand. Might be you might have gone through somewhere else also regarding the zero order system. So you can go through the remaining material from the textbooks. It's very easy to understand and very easy to apply also. The characteristic equation for the zero order system is very simple, and we can very conveniently find the response of this system also. So more or less, if the static sensitivity K is going to remain constant, we call that a zero order system. And the simplest input output characteristics are given by these zero order systems. And now there are say certain issues into this. Say zero order instrument, say for example, ideal zero order instrument is very simple and say very desirable. The reason behind this is very easy in getting the mathematical representation of the system. Right. Actually, there is little deviation from, say for example, now if we consider the example of the potentiometer itself. Theoretically, this is a very simple instrument and very desired, but in actual practice, that the representation of the physical system becomes difficult. Let us understand this. Say if I have got the resistance wire, and at the input I am going to apply some kind of EMF, say EMF here. Because of the flow of the EMF into this and because of the presence of the resistance, it starts giving rise elevation in the temperature because of the resistance being overcome by some amount of EMF is consumed into, and because of this we find the temperature goes on increasing. So I think if you recall the earlier discussion, we said that there is no loading effect present. If there is no loading effect present, then only we are going to get the better indication of the dynamic system. If you recall, in the last lecture, we have seen that there were three different blocks. Say the one system we have seen where there is a primary sensing element, some amplifier, and one more amplifier here, and then we have represented that as a common transfer function with say factor K1, K2, and so we have seen that it's K1 times K2 times K3 with all the values here. So here it is assumed that when there is no loading of the system going to occur, then only this model for dynamic characteristics goes on having proper say anticipation. In this case, it is kind of a loading. The resistance itself is going to take some value of the input. Because of that, there is change in the temperature. Then also because of change in temperature, there is little change in the resistance. So because of this, there is loading effect, and we find that the measurement becomes something apparent, which is not exactly reflecting to the true input supplied. So that is what in actual practice we find the mathematical model is very say approximate. We cannot say that it is going to be a perfect one. Coming to the next part of it, say the slider that is applied with the deflection Xi in case of the potentiometer, the input deflection. Because of the sliding itself, there is some kind of friction in between, and there is say impedance created because of this coil and the EMF passing through. There is some AC field, some kind of field flux is created. So again, some power or some kind of input is consumed there, right? So in all, what you can identify is it becomes very difficult to have the exact representation of the system, first order system mathematically. So those are based on the approximation. Let us understand this. I think few of these I have already spoken. Say voltage measuring device has a finite resistance. Let us say this is a voltmeter, and there is some coil over some magnet. So due to this coil and the finite resistance of the coil, we find it draws current. And then the winding current changes because of this being utilized for overcoming the resistance. Then second condition we can assume the resistance that is here used as a device for measurement of the displacement is not a pure. Say the material may not be consistent, it will have variation in the resistance and so on. Do we assume that between this distance, say first interval, resistance should be del R. In the second, the remaining part, it should be del R1. So del R and del R1 should be in proportion. But because of the non-consistency of the material, it is going to differ. So it may not give the exact indication of the proportional change in the resistance over the length. So it has, because of the winding and the coil, it have inductance, and also it stores some charge because of the, say, residue capacitance. So these are the issues in practice that is going to occur. Now, the variation is slow. Variation in the resistance is going to take some time for arriving at the proper, say, output EMF. So now if we are going to make it dead slow, I am going to make it dead slow, say for measuring the distance of say 2 millimeter, if I am going to take say 10 minutes, very slowly I am going to move, then it is not giving any proper output EMF, right? Then in case of the high speed even, the effects is not negligible. We find if we go on varying rapidly the distance xi, then in that condition it may not reflect properly the output EMF proportional to the say input EMF. Inductance and capacitance can be made very small. Speeds are not high enough. The measurement speed is not suitable for a quick change into the input. And the sliding contact will have some inertia and friction. So there are different issues. So though we are discussing the simple instrument called as the potentiometer, it is very difficult to get the ideal zero order instrument, and that is why we call that as an approximation. The mathematical model approximately represents the zero order system. So the instrument cannot be ideal zero order system, but it is approximated, or the approximated to the zero order system. But still it find more or less say fair results for finding the dynamic characteristics. Now further, I think that issue is left over here. Further, when you will go for the linear measurement devices in the next part of your syllabus, you will find that there are certain issues into the potentiometers. Say though we find ideally the characteristics is linear between the output and the input, we find, say for example, there is a wire. If I'm going to magnify the resistance, the resistance wire, it will have the diameter d of the coil or the wire which is wound over certain say certain rod or certain say support component, and then this is the diameter d of the wire which is wound over. Now multiple terms are made, and the connection that is used for getting the resistance change, say for example slider, will be something like this, and some electrical connection between this and the wire is made. So these are the two terminals. Now you see the smaller diameter will give this distance closer. As the diameter goes on reducing, the distance become closer, more close. And then in that condition, say for example my slider point is moving from say point 1 to point 2, then possibly the distance it will consume, say whatever small distance xi that is applied here between the position of the slider from point 1 to point 2, there will not be a much effective change to the resistance, because at the mid position it will not show the exact amount of change in resistance between the length of the wire which is wound over the rod of diameter d between the 2 points. The pitch distance, if it is going to be small, it will not reflect faithfully the change in the resistance between that length of wire. And then because of this we find there is a, say, approximation. Then this distance will not be faithfully measured, and there is limit how small diameter we can have for the wires. As the small diameter goes on becoming smaller, then we find the strength of the wire goes on reducing. Also the resistance is also going to change. Right, so these are the practical concerns, and because of this we find that the wire wound count kind of resistance are giving the pulse into the EMF. So in actual practice the EMF induced will be something like this, the graph will be something like this. I think this you will find into the linear measurement devices, and then we approximate this to the straight line. Say for example on the winding number 1 it will show some kind of output, then from 1 to 2 till there is a proper contact made, there will be the same value of the EMF shown. Then again from point 2 to point 3, the contact from the wire turn, second turn to third turn, it will again have the change in the output. It is going to remain same, and so on. So these are, if you are going to see in the finer way, we'll find it is not a straight line, but it is having some kind of steps, and that's what we call that as approximation again. So this is because of the configuration. And also you'll find that to overcome this, then we are going to have the continuous resistance in the form of the film. See, if I am going to make a film, a carbon film of given length, a very thin layer, and if I am going to have this as one terminal, this as the second terminal, and if the slider is moving now instantly from one point to the other, we will find it is giving more clear understanding. And then the curve for this kind of carbon resistances, the input output characteristics can be given in the format here. So it will be more smooth, it will have a very small variation here and as good as a straight line. So it will be a very thin deviation or the very small deviation, and then it is better approximation towards straight line. So it depends on the material also. So there are different, say, factors which are going to say that any of the system is going to be zero order instrument. So it is the in all, what is the outcome of this discussion? There is no ideal mathematical model for zero order system. It is better approximation of that, and then within this approximation we find the static sensitivity K, and then we predict the dynamic behavior. We also see that this dynamic behavior can be seen with certain assumptions, certain say pre-assumed conditions, that the resistance is not, say, there is no fast motion of the slider on, that is what is given here, right? So further information, this discussion is better given into the book of Doblin. You can find it out and you can read, go through it. For further references of the zero order system, especially the wire wound and the other kind of the resistances, or the linear and the angular measurement devices given in the book of Doblin, you can refer. Right. So let us move on. So let us understand what is the first order system. Say first order system from the earlier linear equation that we have seen earlier, when the constant other than A0, A1, B0 and B1, except this everything is zero, or they are not present into the equations. So we can give the better representation of the first order instrument in the form of equation, say A1 dQo by dt plus A0 QO equals to B0 times QI, where QI is the input entity and Q is the output entity. So whenever this kind of equation is formed for the measurement device or measurement system, we call that as a first order instrument. Now this becomes very important. Let's try to understand. that our measurement system given to us, we should be in a position to find out what is the input output characteristics, because of which we will be able to classify whether that is a first order instrument or a second order instrument or zero order instrument and so on. Even instrument with higher orders is also possible. Now we are thinking from some different perspective depending on our requirement, that we want to have the measurement of the given entity for the system. We can frame a system with say multiple, say the orders, higher orders also, right? So first and foremost important task here is to break up the system and get the equation to take a decision whether it is zero order, first order or second order instrument and so on. So whenever this kind of equation we will be able to receive from the instrument or the measurement system, we'll be calling that as a first order system. Now, if we are going to simplify this further, we can write it down in this form: the constant A1 upon A0 times dQo by dt plus Qo is equals to then the proportion in terms of the B0 by A0 times Qi. And further we are going to represent these two proportions by certain names. Then we can simplify this and we can put this equation as very generalized equation for the first order system is tau times d plus 1, where d is the operator representing d by dt times the function, plus 1 times the output quantity is equals to k times qi. Now I think this we already defined this in terms of the zero order system, that the value of do upon ao, we represented that as a static sensitivity k. So same we are going to apply it here. So this is static sensitivity times qi, and then this a1 by a0 will be called as a or represented as a tau. So where k is a static sensitivity that we already have studied or we have seen, parameters are same in any order of the equipment. So this static sensitivity is going to remain there as a factor, and unit, it depends upon the input and the output of the system. Then the second constant we represented a1 by a0 as equals to tau, which is called the time constant for the first order instrument. It basically provides some information regarding the settlement of the measurement device for a steady state response or steady state reading that is given. So that is actually a time constant having a time unit. So with this, we can take this as a generalized equation for the first order system in the form of tau d plus 1 times qo equals to k times qi. Right. So the transfer function for the first order equipment will be given as q upon qi in terms of k upon tau d plus 1. So this is a generalized representation again of the transfer function. Any difficulty understanding the term or some mathematical representation of the first order system, first order measurement device and so on? So we are taking reference of that generalized equation, linear equation with constant coefficients again, and then we have found, we have came to certain conclusion that if these are the situation, other than this everything is absent into this, we will be getting the generalized equation in this form, and if this is achieved, we will be able to say that the measurement system is of a first order measurement device. Okay. Let us understand this. Say let us take example of the thermometer as a instrument. Into this, when we are going to dip this thermometer into the bath having temperature Ti of the fluid, and we can say this is the input in which we have dipped the thermometer. Now this thermometer is having a bulb inside, whereas some volume of the fluid is inside it. Say mercury, some volume of the mercury is there, which is at the temperature of fluid TTF, and the sufficient depth if we are inserting into it, we will find the input relationship Ti, and using the value of the length, proportional length of the rise of mercury into the capillary, that is say in the terms of XO. So this is the transfer function that is obtained. Let us understand how that will be obtained. Say, so let us say Ti is the temperature of the medium, TF is the temperature of the fluid in the bulb, and XO is the displacement of the mercury in the capillary from the reference mark. Say for example, this 0 mark on the thermometer. So from this it has raised, and this is proportional to the input temperature Ti. So wherever that has reached, say XO, we are going to formulate the equation. So this equation can be governed by considering the input output characteristics. Say the reading of the mercury column will be given in terms of Kex times Vb upon AC times TTF, where this is the differential expansion coefficient of the bulb and the fluid in terms of meter cube per meter cube degree Celsius. So this is the first constant that is used, Kex. Vb is the volume of the bulb in terms of the meter cube, and AC is nothing but cross section area of the bulb in meter square. So this is a general expression how much the level of mercury will be obtained from 0 mark in the capillary. So we go further deriving the equation between TTF and Ti. So the law of conservation of energy over the infinitesimal time dt is say used here, so that heat in, that is heat input to the bulb or the mercury, will be minus the heat out from the system is nothing but energy stored inside the bulb. So this is the common equation that we are going to use. So heat output will be 0, that is assumed. There is no heat loss. All the heat that is present will be representing truly in the display of the particular device. Heat input is nothing but the one that is going inside the bulb through the heat transfer. Okay. The energy stored is nothing but the temperature rise of the bulb, because of which we have got the value of XO into the bulb, right? So applying this equation, UAB Ti minus TTF is equals to the volume of the bulb times rho C dt TF, where U is nothing but overall heat transfer coefficient. I think this is a very simple equation that we have studied in case of the subject of the thermodynamics in EC1, right? Where AB is the heat transfer area of the bulb, rho is nothing but mass density, and C is the specific heat of the fluid. So using this equation and simplifying it further, we will be able to lead to the further equations, that is Vb rho C dt TF plus UAB TTF dt is equals to UAB times Ti dt. Further solving, we'll get this represented in terms of different constants, right? And then we'll approach to the very close equation that we have achieved already in the, or we have said as a standard equation for the first order system, that is tau d plus 1 times q is equals to kqi. Now we can say correlate this qi as the input, q is the output here, and then we get the different constants. Say tau is nothing but rho c vb by uab in terms of seconds. So that is the first constant we got here. This is the first constant as nothing but tau. And this is the second constant that we have found in terms of the static sensitivity K from this equation. K is nothing but the Kex times Vb upon AC, meter per degree Celsius. And thus we have decided, or we have derived this, that the thermometer is a first order instrument or first order system. Right? There are few more examples of the first order equipments, like the one that is given in the thermal element, and one more, that is the equation or the that I see from this textbook, is resistance transducer configuration that is used in your electronic circuits. Say for example here in amplifiers, wherever we are going to use them, those in combination. Say for example resistance is here and the capacitance is here, is connected to the value of EMF with some resistance. This is from the book the diagram that is given. So the output EMF will be taken between the two terminals, and then this will be the value of input element. So if you are going to derive the equation for this, it also can be obtained in this format of the standard equation for the first order equipment or first order measurement device, right? So very first, I have told you that very first step into this is we need to arrive whether the measurement device or measurement system is into which category. It's a zero, first order, second order, or say higher order system. So assumptions that are made here into this the thermometer, that there is no heat storage into the wall. So if it is there, it will be very small as compared to the value of the heat capacity of the bulb, heat capacity of the mercury into the bulb. Then overall heat transfer coefficient is going to remain constant. If there is some variation, that is negligible, that is assumed here. Where the area bulb is going to remain constant. It remains constant practically, but say there is very minute change into the area. If the thermal expansion coefficient of the glass is considered, we will be able to even quantify that. But it is so small, that is why you find the thickness of the bulb of a thermometer is very thin, so that there will be no effect on the change in the area. So this is assumed, blanketly assumed, that the area of the bulb of thermometer is going to remain constant, there is no change occurring, and there is expansion, the minimum expansion is there, or we can say even zero expansion of the bulb, and the glass element that comes in contact with the thermometer is going to occur. So that is what is assumed, AB is going to remain constant. Then it is assumed that there is no heat loss, even if the bulb is going to take some heat from the system inside the tube. Say for example, this is the beaker, and the heat that is taken by the mercury, and while raising through the distance of XO, no heat is given out through the glass. There is no heat loss, that is assumed. Practically it is impossible, but theoretically we assume that it is there is no heat loss through this mode, and if it is there, it will be very small and is very negligible. So it is actually lost from the stem, the portion that is inside and outside the length of or the depth of insertion. Right. Mass of the fluid in the bulb is going to remain constant. So the fluid rise in the column is very even. The column is the capillary having a constant diameter throughout. There are multiple assumptions. Now why we are discussing it here is we must know the consequences of the possible source of the error in the measurement. Let us assume that any of the system, maybe of zero order, or first order, or second order is there, and we are going to make the mathematical equation for the system. Then we must anticipate what are the possible modes of error. Now in this condition, if any of this assumption that we are taking at the beginning of the experimentation, if those are not valid, if those are having a large impact on the measurement, then definitely there are some errors being introduced. See, let us take an example here. Instead of the glass thermometer, if there is some metal, so what will happen? Once it is dipped into the thermometer, it will start conveying the heat from the system to the surrounding. So rate of heat transfer will be higher in case of the material, and that is what we have to say from instrumentation point of view, or from the measurement system design point of view, we have selected the physical elements into the measurement system such that these effects are minimal, these effects are minimized, or we are moving more closer to the assumptions, the standard assumptions. So there is no heat loss. Now again we assume that there is, other than glass, some other material is taken. Then probably the area of bulb will vary more as compared to the glass. Even theoretically there is some change in the area, it will be more if it is some different material than the glass. Mass of the fluid is going to remain constant. If the element is say metal, then possibly there will be change in the diameter, inside diameter of the capillary. So probably the fluid rise in the column may not be even. So the overall accuracy of the measurement system depends on multiple issues. So that is why we are discussing this in depth, because these are the few sample examples we are samples we are discussing regarding the zero order, first order, and so on kind of the instrument. So it is very important, though we are saying that we are assuming something, we must know what are the effects of the assumptions or the consequences if assumptions are not, say, followed clearly into the design of the system. Now C is going to remain constant, whereas we find practically is going on changing with respect to the temperature. Right? So you can see the consequence if there's some other material is taken, probably this C will not remain constant. Instead of mercury, let us say there is some other fluid used, then it definitely is going to affect. So the assumptions that we have taken, now let us understand the response of the first order system. Now we have arrived at the conclusion that the thermometer is a first order system. The example of the first order systems here, I think just now we discussed, which is nothing but the resistance transducer connected to the display unit or the amplifier of the measurement device. Let us assume now the response, or let us find out the response of the first order system with the standard inputs we are going to apply. Now we are at the second step. The first step, we have got the equation, mathematical equation for the system, and we have decided that thermometer, or we came to conclusion that thermometer is the first order instrument. Now we are going to see the dynamic response of this first order instrument called as a thermometer for the standard test input. Let us see, the first one is the step input. So when the step input is given, we find that the input at the given time, say if I write this as Qi, at this time interval 0. Somebody want to say something? Anything to be discussed? Okay, if it is there, you let me know. Right, I think we have still 5 or 10 minutes to go. We'll take something and then we'll try to bind up our conclusion, the discussion here. So step input, if I have this Ti over the time, at the instance it is at 0 time, it will have 0 input, and at a very small possible time I am going to apply the input to this. So it is the condition, suppose, where the thermometer is in the environment, or in the room temperature, ambient temperature is there, and I am going to dip suddenly that into the beaker in which some fluid at some temperature is kept. So you can assume the thermometer again, and here is the beaker where there is a fluid kept at the temperature, some temperature, let us say T1, which is something else than the ambient temperature. Your thermometer is at ambient temperature. Suddenly we are going to dip it into it. So Qi, at that, before dipping thermometer, it is at 0, say at the particular time with the temperature or room temperature, let us say it as 0 temperature, and then suddenly it is dipped into the elevated temperature at T1. So this is the T1 as the first temperature given. So at Qi equals to Qo, input and the output shown by the instrument will be the same at time interval equal to 0. Now at the next interval of time, we are going to apply the step input Qis, so that we are going to wait for the output shown by the measurement device. So here the characteristic equation is tau times d plus 1 times Q, KQs for t greater than 0. This is what is our generalized equation for the first order system. So here we will be getting two different parts. Output, the component of the output in terms of the complementary function, and then there will be one more, it is a particular integral on solving this equation. So these are the corresponding parts of the solutions, QOCF and QOPI, and the total equation, then QO is now C times minus T by tau plus K times QIS will be obtained. Now let us say at the 0 instance, the QO will be 0. So this is the first boundary condition. I should say that equation A indicating the boundary condition 1. At time interval 0, there is output also 0. So we can find the value of C. The constant can be found out. So the constant will be equal to minus K times QIS. Right. So the equation can be rewritten. The final equation can be rewritten in the form of equation B, which is by putting the value of C into the equation minus K QIS times e raised to power minus T by tau plus K times QIS, where QIS is the step input. So in this one we can obtain the value further simplified is 1 minus e raised to power minus T by tau times QIS times K. So the response QO upon KQIS now will be equal to 1 minus e raised to power minus T by tau, which is nothing but a dimensionless quantity. Right. So step input will give two different formats, say complementary function and the particular integral, the part of the solution, and on combining and getting the value of constant C, we can represent the response of the system to the step input will be something like this. Now that's what we are about to discuss here. Say the diagram that I have shown in the next slide to be discussed from here only. Say if I show on the same graph or I use other graph now. This is, say, let us say QO and this is the time T. Then response of the system, your input was something shown by dotted line. This is nothing but value of your QI. Now QO, it will take certain time. It will start building the settled value. It will take some time to rise and then it will show the steady output. So this is what is the response. As far as output is concerned, this is nothing but output, whereas this was the input. So response of the system to the step input will be something of this nature that is shown in here. This will be KQIS. This is the output quantity now. And then this is the one that is shown here. Now it may, depending on the constant, the first constant tau, the response of the system, if there is a large time required, constant time tau, if it is going to become large, we find that it will be slow. It will take longer time to come to settled value or settlement value. Smaller value of tau will give a quick settlement of the output of the instrument. Right. So we find that from this graph, the tau or time constant is going to decide the response, how quickly the first order system is going to respond to the step input given. That will be represented here. And thus this becomes a very important property as far as the first order system concerns. Say for example of the thermometer, we desire that this value should be as small as possible so that it will give better indication of the temperature, change in the temperature. It will be very easily giving the even small minute possible change with respect to time will be sensed by the thermometer. Now if we are going to plot the graph between the Q upon KQIS, the last equation that we have seen here, sorry, this one, say if I call this as equation C, if I take into account QO by KQIS from this equation C, we can represent that in terms of graph QO by KQIS over T by tau. Then the ratio of T by tau and QO by KQIS, we find that it goes on varying for T by tau, varying from 0 to infinity. And then we find the different values. Say 1, it represents this as 0.632. So for 1, as say T by tau, we find around 63% of the input value is being represented in the display of the device. Whereas for the time constant equals to 2, the ratio of T by tau equals to 2, we find it is 86.5% of the input is reflected in the display device in the form of or the output or the displayed output. Then it is 95%, 98% and so on. So onwards you find it is very small change. It means almost we are reaching the settled value of the output being displayed. Right. So what this indicates, T by tau indicates a very important parameter which is going to define the response of the system in regards to the quickness of capturing the given input in the form of display. Right. Now, if we take, I think this will discuss in some later consequence. I think in the next slide is given. So let us come to the part that is say tau. I told you in the earlier graph that the tau becomes very important. If the tau is going to be large, it will take larger time to set with the desired output value. Okay, so I think we'll continue for 5 minutes. We'll take this as a last slide and then we'll stop. So the settling time is nothing but the time for an instrument or the measurement system to reach and stay, to reach the value and to stay there for the minimum desired output value. So within the stated plus minus tolerance band around this final value, if you again recall the earlier graph, so for example, this is the standard input given. Now wherever it has come down to a very settled value and it is going to stay there, there is no further deviation either coming down or moving ahead. So this is the minimum output that the instrument needs to display, and the minimum time, let us say I call this as T dash. So this time T dash is nothing but my settling time. So small settling time is the say prediction that it is a quick in giving response. It depends on the percent of the tolerance band. Now if I select the tolerance band, say for example I allow the tolerance band to be varied, say from this to this. If I take 10% value, somebody of you can take say 5% value, 2% value and so on. This is what is your expectation, that it should set within 10% of the value or 5% of the value or 2% of the value and so on. So settling time is related to the tolerance band. Smaller the band, you will find the settling time will be something larger. If I consider that this value to set here for say 20% of the reading, 20 plus minus 20% of the input, then preferably this T dash will be smaller. So that is subjective. But then there is a common agreement that some minimum value of the tolerance band can be estimated, should be estimated. So essential to mention the tolerance band. So it is say agreed upon, a general agreement that it should be in the plus minus 5% of the tolerance of the output. So either 95% or 1.05 times the output should be shown. As it is step input, it will never show higher. So 95 means at least 95% of the input should be reflected in the output reading. Then wherever it reaches say 95% or plus minus 5% or minus 5% of the band, the time T dash will be called as settling time, which is equivalent to 3 times the constant tau. So this is important to understand. You try, if there is doubt into this, you please ask me. What I say is settling time is nothing but T dash as represented in the diagram, which is corresponding to the given tolerance band of output being displayed. Now if I agree upon, or we agree upon as with a say common understanding that it should be plus minus 5% of the output, that is minimum 95% of the output should be reflected on the instrument panel display, then that will be called as a settling time of the first order system for step response, and then that is ideally considered as 3 times the tau. So we now can anticipate the value of tau that instrument should have. You go reverse way now. Suppose we are going to create a first order system and now we want that instrument should reflect the output, 95% of the output. We can find out the value of tau. Numerically we can find out tau and we can then move ahead for finding further details of the instrument. What shall be the bulb diameter, and so that can be found out in the reverse order. Now let us discuss if to reduce the tau which is desired for faster response. In case of thermometer, what are the issues now? We have to reduce the value of rho. You can see from the equation as the value of the density goes on reducing, your time constant goes on reducing and the response will be quick. We can also achieve this by varying the value of C, by lowering down the value of C and bulb volume. Also, this can be achieved by increasing the overall heat transfer coefficient and the area of bulb. Right. So I think we'll come again in this points to discuss in the next class. Right. So I think next class will be on Monday, and I will ask you to go to the textbooks. Minimum first order instrument and step, all the kinds of response on the first order system will be asked in your sessional examination. So some part is there as a self study for you. We are trying to cover that in the coming class, that is on Monday's class. But you can start say looking at the different numericals or different mathematical treatments on the at least first order system. Zero order system, first order system, all numericals on that you can find out from the textbook. Start studying those. So I declare the portion for your sessional examination that will be minimum up to the first order response, first order system for all kind of response. Step input, ramp input, then the sinusoidal input and the impulse input. So we'll again come back to this point in the coming class. Any doubt? Anything you want to ask?
Sir?
Yes, please go ahead.
Sir, actually, our college is open. We are allowed to come from 21st March, right? So,
right.
How are you going to take the classes in the hybrid mode?
Then only. Say why it is so, because I hope the remaining portion after your sessional 2, that is after the dynamic characteristics complete, first order, second order, and new mathematical treatment on that, the remaining portion will be taught by Thakre sir. So if it is in the physical mode, then he'll have to teach both. So I think that will continue for this semester. I think this is what is my anticipation. That will be on online mode only. Right?
Okay, sir.
If there is some change, then I will be able to inform you. Otherwise, this goes with this understanding only.
Yes, sir. Thank you, sir.
Okay. I think we'll stop here for today. Thank you for joining.